Welcome to This Explainer. Okay, think about time for a second. We treat it as absolute, right? Constant, perfectly measurable. But what if time itself has a fundamental blurriness built right in? What if the universe literally prevents us from ever building a truly perfect clock? Well, today we're breaking down a mind-bending new study that explores exactly that.
Here's our roadmap. We're going to ask if time is actually flawed, dive into the whole quantum measurement problem, look at spontaneous collapse and gravity, uncover a hidden limit to precision, and finally, see how this might just unite the universe's biggest laws. Let's get into it. Starting off with Section 1, is time actually flawed? The mystery of the perfect clock. So, is there a literal twitch in time? The Foundational Questions Institute, or FQXI, has been backing an international team of physicists who are taking a really hard look at quantum collapse models. And what they're finding hints at tiny time fluctuations. This basically suggests that a perfectly exact clock might actually be physically impossible to build. They're talking about a fundamental limit to how precise time can ever be. Now, please don't go using this as an excuse for being late to work. This blurriness is incredibly small. We're not talking about your morning commute here. It's more of a tantalizing clue to the deepest, most fundamental laws governing our universe.
Moving right along to Section 2, the quantum measurement problem, why reality is blurry at the micro level. To really understand where this flaw in time originates, we've got to zoom way down into the microscopic world of quantum mechanics. At these super tiny scales, particles do not behave like the everyday objects we're used to. Instead, they exist in a state of superposition. That basically means they have the ability to exist in multiple states or even multiple places all at once, which physicists describe using a mathematical object called a wave function. And this creates a massive theoretical clash. On one side, you've got the mathematical fuzziness of quantum superposition, where particles are just existing in multiple states at once. But on the other side, you have our daily reality. In everyday life, objects occupy one definite place or state at a time, right? Your coffee cup is on your desk, it's not simultaneously chilling in the sink. This gap between the quantum and the classical world is a huge headache for physicists. So, how do we usually bridge that gap? Well, the standard fix is this idea that observation causes wave function collapse. Basically, scientists usually propose that when a quantum system gets measured or interacts with an observer, its wave function suddenly collapses down into a single definite outcome. Honestly, it's always been a bit of a clunky idea, this notion that human observation somehow forces the universe to make up its mind. Which brings us to Section 3, spontaneous collapse and gravity. And here's the plot twist. What if no observer is actually needed? See, there's an entirely alternative explanation out there that bypasses the observer completely. Back in the 1980s, researchers started cooking up theories where this wave function collapse happens spontaneously, just totally on its own. Recently, an international group of researchers examined two of the leading versions of these models. There's the Penrose model, which is super interesting because it links gravity to the collapse of the wave function, and then there's continuous spontaneous localization. Nicola Bortolotti, a PhD student at the CREF Research Center in Rome, who actually led the study, puts it perfectly. He said, "What we did was to take seriously the idea that collapse models may be linked to gravity, and then we asked a very concrete question. What does this imply for time itself?" I mean, that is just a brilliant way to take a purely theoretical idea and apply it to the actual physical nature of time. And that perfectly sets up Section 4, a hidden limit to precision. Why perfect timekeeping is impossible. The research team published their findings in Physical Review Research, and they actually established a quantitative relationship between these spontaneous collapse models and space-time itself. It breaks down into 3 clear steps. Step 1, spontaneous localization occurs, so the wave function collapses on its own. Step 2, this spontaneous process, which is linked to gravity, causes space-time to subtly fluctuate. And finally, Step 3. Because space-time is fluctuating, time itself gains this extremely small inherent uncertainty. The ultimate takeaway here, time literally cannot be perfectly exact. Now, if hearing that time is inherently blurry makes you a little nervous about the fabric of reality, check out this follow-up quote from Bortolotti. He says, "Once you do the calculation, the answer is clear and surprisingly reassuring." I love that he used the word reassuring. Basically, this inherent uncertainty isn't going to break our everyday reality. In fact, the uncertainty is many, many orders of magnitude below anything we could ever currently measure. Researcher Catalina Cristiano points out that this has zero practical consequences for everyday timekeeping. And her colleague Christian Pishikia adds that modern technologies are entirely unaffected by this. So even the most advanced atomic clocks we have on Earth, totally safe from this quantum fuzziness. Timekeeping is still absolutely one of the most stable pillars of modern physics. Finally, let's zoom back out to the big picture with Section 5, uniting the universe's laws, bridging the micro and the macro. This discovery matters so much because we've been hitting a massive roadblock in the future of physics. We have these two incredibly successful, yet completely incompatible frameworks for understanding the universe. You've got standard quantum mechanics describing particles at the microscopic scale, and general relativity explaining how gravity shapes massive things like stars and galaxies. The big problem, they treat time completely differently. Quantum mechanics treats time as this external, constant parameter, but general relativity, it describes time as dynamic, stretching and bending under mass and energy. Catalina Curcianu summarizes this core issue perfectly. She says, in standard quantum mechanics, time is treated as an external, classical parameter that is not affected by the quantum system being studied. So standard quantum mechanics basically just ignores the flexible, bendable nature of time that Einstein proved with relativity. They literally just don't speak the same language. And this is exactly why this points us toward a deeper theory. By exploring these unconventional collapse models, this FQXI-supported research is acting as a vital stepping stone. They're actually establishing possible mathematical links between quantum behavior, gravity, and the flow of time itself. It shows that these radical ideas about quantum mechanics can actually be tested against precise physical measurements. And that gives us a clear path forward to maybe finally unify these stubborn theories into one cohesive framework. So this leaves us with a truly profound question. If quantum weirdness quietly blurs the precision of time, what other fundamental laws are hiding in the fuzzy edges of our reality? It is absolutely fascinating to think that the very act of the universe rendering itself from probability into reality might cause time to ripple and blur. I really hope this explainer sparked your curiosity and gave you a whole new way to look at the clock on your wall. Keep questioning the fundamental nature of the universe, and we'll see you next time.